Hey there, everyone. Thank you so much for joining us today. As we let people kind of filter into the Zoom room, please go ahead and use the Zoom chat box at the bottom of your Zoom window there, and just let me know if you've been to one of our webinars before. I'd love to hear from you. And make sure the toggle is set to everyone, so you send the chat to everyone and we can kind of see who's been here before, who hasn't. It looks like Rick has joined us before. Hey, Rick, thanks for coming. Anyone new? Not sure what to expect? Oh, Laura, nice to meet you. Oh, I'm so glad to hear that you feel our webinars are useful. Very great. So it looks like we have a nice mix of new people and people joining us again. That is so awesome. And I want to make sure that we get to all of the fantastic physics learning opportunities we have in store today. And so I'll go ahead and jump into my spiel, as it were, and then I'll hand you off to today's presenter. Really, I just wanted to check in about two things. First of all, please put any and all questions right there into the chat box. I will keep an eye on the chat box and reply to any questions that I'm able to. We also have the fabulous Dave Vernier online, and he will be answering questions in chat as well. So please let us know if we can help with anything or if anything needs a little bit more describing. And yeah, just put it in the chat. And the second item that I wanted to touch on with you all is that we will be sending a recording of today's webinar as soon as it is live on our website and on YouTube. That'll be about 3 to 5 business days. So keep an eye on your inbox and I will send that off to you as soon as possible. In a moment here, I'm going to drop a resources folder for you to use. That will also be in my follow-up email, but you can hold on to the link until then. That just has some helpful experiments and other materials that Josh shared with us. So keep an eye on the chat. I'll put it there. And with that, I will pass you off to Josh. And thank you again for joining us.
Hi, everyone. It's great to have you here. I'm excited to talk to you about the motion detector today. To give you an idea of what we're going to do today, we are going to talk about a number of things, all things motion detector. And we'll start off just with a quick poll. I'll introduce myself and my co-presenter, and I want to know a little bit about you. We'll talk a little bit about the motion detector itself, like how it works, and some of the tips and tricks that you might want to use when using a motion detector, just because of the way it works. And then I specifically want to talk about 3 particular activities that use the motion detector. They kind of show off the versatility of the motion detector and are great activities in and of themselves. And then at the end, we'll probably have 5 or 10 minutes to answer any questions that have come up during the webinar that we didn't discuss then. All right. So Dylan's gonna put up a poll right now. And while you're answering that, let me just tell you a little bit about myself. My name is Josh Ence. I've worked for Vernier for about 9 years now. Prior to my working at Vernier, I was a high school physics and engineering teacher. And in my classroom, I used Vernier products. I used these motion detectors, and I really loved how easy it made all of our lab work. Did a lot of lab work. I love doing experiments and that sort of thing. I feel like that's how students really learn it best. At Vernier, I do things like teacher trainings like this. I do a lot of customer service stuff. So if you call or email or get on our website and go to the chat and have a question, it's like I'm one of those people that's likely to answer your questions. I get to go to a lot of science teacher conferences like NSTA and AAPT and that sort of thing. And I get to help out as well with product development. You know, I talk to a lot of teachers, and I hear what you want and what you need. Meeting or helping out today in the chat is Dave Vernier, the co-founder of the company and the best lab assistant you could ever hope for. Dave, you want to introduce yourself?
I'm Dave, just glad to be here to help. I'm mostly going to watch the chat. I'll probably pipe in and make a comment or two.
Dave will answer your simple questions there in the chat. If it's something that's something I've missed or whatever, he's just going to interrupt me, and then I can give an explanation to everyone. So the Q&A, the chat is where you'll put any sort of questions. During the webinar today, I'm going to do all of my data collection in Graphical Analysis. Graphical Analysis is our kind of our cross-platform app. It works on PCs, Macs, Chromebooks, tablets, so like Android or iPads, that sort of thing. It comes in kind of like, if you just download, access Graphical Analysis, that's the basic version, it's free. There is a Graphical Analysis Pro that's like a paid license. If you want to learn, especially if you're new to Vernier, this is probably the app you're using. If you're a long time Vernier customer, you probably are familiar with our Logger Pro software. If you want to learn more about what graphical analysis is, you can go to the link there. That's up here. Graphical analysis is nice because we have downloaded versions. Like I'm going to use the downloaded version that works on the PC that I'm on here. But there's also a web version that just runs within, runs within your browser. So like I said, that web version, the downloaded versions, it all looks and feels the same, whether you're on an iPad or a computer or your smartphone, and it kind of all works the same. We usually point people towards computers and Chromebooks and stuff like that, just because it's nice to have the bigger place, but it works just as well on your phone. As I go through this, most of the labs that I'm going to do today, you could use the basic version, no problem. And there are only a few features here that are especially helpful, a few pro features that are especially helpful when it comes to motion detectors. I'll highlight those as we get through this. So kind of as a bit of background, there are lots of ways to measure motion in your physics classes, right? Probably the easiest way is a meter stick and a stopwatch. I did that a ton in my classes. Just, we want to measure how fast you walk. We just pull up meter sticks, mark a couple of hashtags on the ground, and use a stopwatch to time people. And it's cheap, it's easy. You probably got a whole bunch of meter sticks, a whole bunch of stopwatches already in your classroom. But if you want to get a position versus time graph, it's kind of a long process. You've got students, they have to create a data table. They're recording position versus time, and then they've got to draw it out and plot it out, and then probably draw a best fit line. It's a lot of steps. And so the probes and sensors, they really get you to the data much faster. But there's still a time and place for that process of using a meter stick and stopwatch. I found that with most of my classes, I could go straight to a motion detector and get good data and get into the conversation really easily. With my conceptual physics classes, I found those students especially, we needed to do this process with just a meter stick, a stopwatch, a couple of times for them to really understand what that position versus time graph meant. I usually use the constant velocity cars, the tumble buggies, they just kind of travel at a constant speed. You put a couple of C batteries in there. And for our stopwatch, I usually used like an online metronome that would just talk every, tick tock every second. I'd set it to 60 beats per second sort of thing. And then they would put down like a washer to mark the position of the tumble buggy every second. And then they go out and plot it out. I found that them actually going through that step of dropping the washer every second and then measuring it out and writing out the data table and then taking that data table and making it into a graph really put together the idea in their brain that the numbers, that the points plotted on this graph are where the object is at each moment of time. If we just went straight to the motion detectors in the software, sometimes that got missed. They could kind of interpret what it sort of meant, but it got a little fuzzy in there. So we would usually do it a couple of times like that before we went to the motion detectors. Photo gates are also a very popular way of measuring motion. They're pretty easy to understand. It's this gate, and that it's going to measure how fast the object is going through the gate. And so you can say right here, it was moving this fast. I've got a photo gate over here, right here, it's moving that fast. It is a little bit tricky if you want to get that position versus time graph. It's great if you want to measure the speed of the car as it leaves the bottom of the ramp. But if you want a position versus time graph, which is often kind of like the mathematical model that we use when we talk about kinematics and dynamics, it's kind of hard to use a photo gate to do that. You have to use picket fences, and then you have to then there's that whole conceptual leap of, well, what is this picket fence doing, and what are all these clock times? That leads us to the motion detector. Motion detectors are really versatile. You can track lots of things with them. They're pretty fast in order to collect data. You get this nice position versus time graph right off the bat. Because of the way these work, there's a little bit of setup and some things you need to pay attention to in order to get good, clean data. This one I'm holding right now is called the Go Direct Motion Detector. It's kind of our latest and greatest motion detector. If you have these in your classroom already, it's probably like, this is our motion detector 2. It's green. It's got kind of like a pivoting head on it here. These two serve the same purpose. How they connect to your device is a little different. The Go Direct Motion Detector connects via Bluetooth or USB, and the Motion Detector 2 here, you need to have an interface like this is an old LabQuest Mini of mine. You got to connect this to your interface and then connect your interface to your computer in order to use a motion detector like this. You might have seen ones like this that are different colors. We make a version that is black called a Go Motion. There's also a version that's gray called a CBR or CBR2. If you have a version like this that's kind of a dark blue rather than this forest green color, that's an old version. This is the motion detector 2. That was the just original motion detector. And then the last kind of way to measure motion is, often we do cart and track experiments. I'm going to show one today, but we have some newer probes that do motion sensing just for that. So there's our motion encoder carts. This is a Go Direct sensor cart. So it's Bluetooth, USB, and it has an encoded fifth wheel on the back, on the underside here. So as it rolls, either on a track or just on a tabletop or the floor or something like that, it tracks its own motion and then transmits that motion data to your device. These are really cool. They've got this is like a rolling physics lab right here. There's so many options that you can do here. It is, of all the options we discussed here, this one is the most expensive. And it's obviously it only tracks the motion of the cart itself. We're going to use the motion detector today to track my motion or to track the motion of a ball, or later we'll do it with a cart as well. But so there's kind of trade-offs there. Like I said, I really like the motion detector. Often when physics teachers ask me like, well, what do you recommend I get? I'm just starting off here. I usually point towards the motion detector just because it's so versatile.
Josh, I might just jump in and just say the other advantage of the sensor card is it does include those other sensors, the force sensor and the accelerometer. So in some cases, it can be a better value.
Yeah, it's got a force sensor built into the end here. This has got a bumper connected there. So like, for instance, at a momentum impulse experiment, you can have it bounce off a wall and you can get force and motion data all at once. It's really cool. These are cool. All right. Let's talk a little bit about how the motion detector works. So the thing that you notice that the most obvious thing about the motion detector, first thing they see is this kind of gold foil transducer here on the front. And it looks kind of like an eye. This is like, sometimes people call this like think of it like Cyclops, like this eye here. But this gold foil transducer here is actually more like an ear. It's a high sensitivity microphone. And it's listening for a particular sound. When this is running, you'll hear it clicking, and it's actually sending out an ultrasonic pulse. It's something like 40 kilohertz or something like that. And this transducer is listening for the reflection, for kind of like the echo of it. It knows it starts a clock when it sends out that pulse, and then listens for it to go out and come back. and it records the round trip time for that sound wave. Then it takes that time and converts it into a distance, right? You might think that this motion detector, the clicking that you hear is the click that it's listening for, but it's not actually. The click that you hear, the click it's actually listening for is it's ultrasound. It's beyond the range of human hearing. The click that you hear is actually kind of like the plastic case of the motion detector itself, just kind of reverberating with the click that it's making with that ultrasonic pulse. And because of that, because the case itself kind of resonates with it, there is kind of a minimum distance at which this works. And for most of our motion detectors, it's about 20, 30 centimeters. If the object is too close, that reflection, the sound reflection, comes back so fast that the motion detector doesn't know whether it's hearing a reflection or whether it's hearing the case itself reverberating. And that distance is about 20 centimeters. If you have the old motion detectors that are blue, that's more like 50 centimeters there. And the difference is primarily that the case itself is a different plastic and it reverberates differently. The reverberation is longer. Another thing to know about the motion detector is that, you know, you think it's really an ear, but it's an eye in the sense that it's like directional. It's looking for the reflections coming from in front of it. You know, it's not a two-dimensional motion. It's really a one-dimensional thing. And the way that we usually describe this is if you imagine a cone that has like a vertex of about 30 degrees, and you imagine that cone, the tip of it centered on the middle of the gold foil transducer, the motion detector can kind of like see anything within that cone. So, you know, if you're close to it, it's pretty narrow, but as you get farther and farther away from it, that cone gets bigger and bigger, and you kind of have to be mindful of what might be inside that cone. So that's kind of like how it works. And that leads me to a couple of tips about your setup. The first thing is to be mindful of the environment in which you're using the motion detector. Anything within that cone, you can see might cause like confusing reflections. So when I did the graph matching activity, I'll show you here in a few minutes. When I did that in my own classroom, I rearranged the desks so that we had kind of like lanes, you know, like bowling lanes kind of thing. And I always told the students that you need to keep the lanes clear. We didn't want backpacks in there. We didn't want tables or straight chairs. We didn't want any of that inside the lane. And that the only thing in the lane should be the person, you know, and as long as they did that, we usually got pretty good data, and it was pretty easy for them to understand. When you're doing like a cart and track experiment, especially if you've got a crowded lab bench, it's easy to kind of push your Chromebook up close to the track itself, but you got to be careful just because the reflection off that Chromebook might mask the motion of the cart that you're trying to track. So you got to be mindful of the environment there. Sometimes we run into odd things. There was one classroom I taught in, one corner of the classroom, I never got good motion detector data by. And my only guess is that there was the furnace was relatively close, you know, like the AC furnace kind of was in that corner of the room. I don't know if it was producing some sort of noise along those lines. We've heard reports of somebody, a student that had a hearing aid, like one of these bone conduction hearing aids, and they found that if they were on the wrong side of the motion detector, it would mess things up. So be mindful of the environment. The second part is the other flip side of that. Be mindful of the target. What are you trying to track? For the most part, hard, flat surfaces, just like if you wanted to make a good echo, are really good for that sort of thing. When I do my graph matching here today, I'm going to use a physics textbook. I'm just going to hold it in front of me because it makes for a nice reflection. Bodies, people generally work pretty well, but that gives you a little bit of a sense more for where exactly is it tracking. If you want to track a ball, this is the ball I'll use for our ball tennis activity. It's good. It's about an 8-inch diameter Nerf ball. It works pretty well. Anything smaller than say a softball might be a little hard to track. If the object is too soft and squishy, sometimes it absorbs the sound waves better and you get kind of a weak signal off of it. So you got to be careful about your target. And the last thing is there are a few settings you can change on the motion detector itself in order to get better data. On the Go Direct Motion Detector, there's a cart mode. At that point, it's kind of like it's looking for quieter echoes, quieter reflections, because it's expecting a cart out there, which is a relatively small target. And so the kind of like the threshold at which it says, oh, I heard a reflection, is lower there. On these older motion detectors, the ones with the pivoting head, there's a sensitivity switch behind the head. And usually it's on this, like it has a little picture of a person and a ball. Usually it's on that setting. There is a cart setting. That's the other, that kind of that lower, higher sensitivity setting. Some people find that even on the lower sensitivity setting, like the regular setting or the not cart setting, it's still too sensitive. And they'll take a sock and put a sock over top of it to make it less sensitive. The Go Direct Motion Detector has one more setting that's a little bit, I don't know if you'll ever use it. It's a temperature compensated setting. And you know, the way that it figures out how far away the object is it takes a round trip time and then divides that, takes the speed and divides by that to find a distance. Now, the speed that it's using is your standard 343 meters per second, you know, the speed of sound in air at room temperature. But if it's warmer or colder than room temperature, that speed is not very good. And so the temperature compensated setting actually measures the ambient temperature. There's a small little temperature thermistor in this, and adjusts that speed for the temperature. Now, for the most part, if you're in your classroom, you don't need to worry about that. But if for whatever reason you were going to take this outside, you're measuring something outside, and it's a warm day or a cold day, you might use that to get more accurate results. All right, so we want to be careful of the environment. You want to be careful of the target, and you want to use any settings as necessary. I'll talk about each of those a little bit with the activities that I want to demo for you today. All right, the first one is graph matching. This is a real fun activity because it gets students up and moving. For a long time, I used this as one of the first things I would do at the very beginning of the year, the first day of school. I loved getting students up and moving right away. It kind of set the expectation for what our class would be like together. And the way that you do this, typically, if you have these wired motion detectors, you're going to put the motion detector on the edge of a table, and students are going to move back and forth in front of the motion detector, and it's going to track their motion. If your students have like iPads or they're using their phone or something like that, and they're using a Go Direct Motion Detector, typically in that case, they would hold both the device and the motion detector together, and then they point it at a wall, a nice hard flat wall, and move back and forth in front of the wall to track their motion that way. One thing that you might do is you might use like a book or a mini whiteboard, or so I have a bunch of whiteboards in my classroom, to use as a target. That makes it really easy for students to understand, like, where exactly on my body is it tracking? Well, it's tracking the book, right? Another thing that can be helpful is, you know, you might mark yourself or have them mark on the floor where 0.5 meter from the motion detector is, where 1 meter away from the motion detector is, 1.5 meters, and so on and so forth. That just helps them kind of get a sense for what where they need to be. So what I'm going to do, one thing I'll note here, I'm going to stop this guy here real quick. One thing you should know is in the folder that Dylan shared in the chat, you'll find a copy of this lab and the teacher notes for this lab. You know, the lab itself has some preliminary questions. It talks about the procedure, kind of steps them through this process. It has them do position matches and then velocity matches as well. You'll notice it has both the method where they're pointing the motion detector at the wall and moving themselves, and then the other option where they've got the motion detector on the tabletop and they're just kind of moving back and forth in front of it. This lab is the very first lab in our Physics with Vernier lab book. And if you own that lab or you purchase that or own that book or purchase it, you get a PDF like this, but then you also get a Word document version so that you can edit it as necessary. I found that most of these labs are great the way they are. but I want to tweak it to fit my particular style and my particular curriculum. So I would take the Word document version and edit a little bit every year. The teacher notes for this particular labs has things like standards and equipment tips, a lot of things that we'll talk about here in this. It has some sample data and that sort of thing, and will help you kind of answers to the follow-up questions and that sort of thing. This particular lab, the version is written for graphical analysis with motion detector, or the Go Direct Motion Detector. When you purchase the book or own the book, you also get all the other versions. If you're using a LabQuest interface, or you've got an older motion detector and you're using it with Logger Pro, all the instructions, all the various versions of those instructions are there. All right, I'm going to pull up graphical analysis now, and I'm going to demo this for you. I will probably embarrass myself when it comes to the actual graph match, because it became very clear to me earlier today when I was practicing that I am very much out of practice. All right, so in graphical analysis here, I've just opened it up, and I get this screen where I can choose how I want to use the app. I'm going to do sensor data collection, and I want to connect to my motion detector. Now, on a Go Direct device like this, I'm connecting wirelessly. You can just plug it in USB if you want, and then you don't have to go through this screen here. But I'm doing this via Bluetooth because the ports are a little bit far away from where I want to be. And there's a unique ID on each of these sensors. This one happens to be just above the barcode here on the bottom, and it ends with an S or with a Y1. I can see that this motion detector here listed amongst the wireless devices ends in Y1. That's the one I want. So I'm going to hit connect. And when I do, it starts ticking. It starts giving me a live readout. I'm going to hit done. I'm going to do a quick tour of the graphical analysis app here. Make this bigger for everyone. So in the upper left-hand corner, this is where you have your file menu, where you could save any data you collected, that sort of thing. Top middle is the collect button. I can just hit collect here, and it's just going to collect some data for me. It's apparently the ceiling is a little over 2 meters away. And the upper right, I've got some options for like some of the more advanced options, data sharing and replay. This box of boxes, I think this is the view options. This is where you can do things like you see the data table, or if you want to have a meter, you want to see the live readout bigger, that's where you see that sort of thing. This overflow menu, 3-dot menu, is kind of where you get things about the app itself. In the lower right, there's a little icon that it's supposed to look like a temperature probe. This is where you get back to this devices, the sensors you have connected. And next to that is a little menu, a little live readout of any sensors you've got connected. Here it gives me the position. If you click on that, you get all the options to adjust the sensor reading. So for instance, calibration, zeroing, that's right. In the case of the motion detector, you can also reverse it if you'd like. And then in the lower left-hand corner, you have your data collection settings. This is where you might change the duration or the data collection rate and that sort of thing. For this particular app, we don't need to adjust any of the data collection settings. And in many cases, you don't have to. All right. So what I want to do is I want to do this graph match lab. And the way it works in graphical analysis is it's going to generate a graph match for me. Because I have a motion detector connected, if I go to this graph options menu, it looks like a graph with 3 connected dots. This is where you would do things like curve fitting and statistics. But because I have a motion detector connected, one of the options is to add a graph match. And I can choose position or velocity. I'm going to choose position. And it gives me a position match. This gray line here is my target. And I'm going to try to match that as best I can. If I were to choose that again and say I don't like that particular one, it's just going to generate a new one. And if you do this a couple of times, it's pretty easy to see that the pattern is it always gives you 3 kind of linear line segments. And that's kind of how the lab is basically written around those particular, that idea that it's all linear line segments, and students are kind of figuring out just the basics of reading and interpreting graphs. If you find a graph match that you particularly like, you could save it, save that file and give it to your students. And when they open it, it'll have just that graph match in it. But if you use that add graph match option, it's just randomly generated 3 linear line segments. I'm going to try this one. I don't know if I have enough room behind me to get this far, actually, so maybe I'll try one more. Yeah, okay. So I'm going to switch my camera here real quick. I am going to put my motion detector here on the table. I've marked a position for it mainly so it's little, and I've marked on the floor down here where 0.5 meter away is and 1 meter and that sort of thing. And I'm going to hit collect, and then I'm going to move back and forth in front of the motion detector and try to match this as closely as possible. I can tell, it looks like I start a little bit more than, or almost 1 meter away. That's about right here. I'm going to use my textbook as, oh, I'm going to do one more thing actually. I'm going to use the textbook as a target, but I want to be able to see, my eyes are not what they used to be, and I want to be able to see my position a little bit clearer. Okay. So I start a little bit, almost 1 meter away, and it looks like at first I'm going to walk towards the motion detector, and then I'm at around 3 seconds, I'm going to turn around and move away from it. And then at about, what, 6.5 seconds, I'm going to move back towards. So that's my plan. I'm going to hit spacebar to start data collection, move back towards here, and move away. And then back towards, and there we go. All right, I'm calling it good. You'll have some students that will get almost obsessive about this, and they'll get really good at it. They'll be able to follow the line exactly. And it can be pretty fun. Some students, some teachers want to do a score and figure out exactly how. I've never been into that. The process here is to learn to read and interpret graphs, position time graphs. I was never very strict about how closely they had to match it, but they did have to be able to tell me, describe it in words. And I feel like that's kind of the point is you want students to be able to see a position time graph and be able to translate that into words. What does this motion mean? Like, is it speeding up, slowing down, moving towards, moving away, those sorts of words. And ideally, you want them to be able to translate that into math, like an equation for a line or a curve or something like that.
Hey, Josh, you got kind of lucky that time. The slopes were all about the same. So you didn't have to worry about your speed, but that's another big thing. If they see a steeper section, they should appreciate that means faster.
Yeah, exactly. And you'll find that students get really good at position matches. And then the second half of the lab has them do velocity matches. And a velocity match, the graph it looks much different. Here, I'll pull one up here for you. And it's much harder to match because it's not a position of where you need to be, but rather of how fast you need to be going. So it's a lot trickier. It's a whole mind change. I often did not do velocity matches the first time we did graph matches. That usually we would talk about position time graphs. We draw a bunch of them, and then maybe a week later we'd start talking about velocity graphs, and then I would have them do velocity matches at that point. All right. I'm going to go back to my slideshow here and make sure I didn't miss it. All right, yep. The next one I want to talk a little bit about is ball toss. This is kind of like, you first usually you talk about uniform motion, kind of like constant velocity motion. And then you want to start talking about acceleration, things speeding up, slowing down. So maybe you're rolling balls down a ramp sort of thing. And then you want to talk about the acceleration due to gravity, and you want to show that it has that same parabolic curve that you get from, or the parabolic curve that you get from accelerated motion, but it's always at a certain rate. And ball toss is this same idea. In this case, we're going to put the ball or the motion detector on the tabletop, have it pointed up towards the ceiling, and we're going to track the motion of the ball as it goes up and comes back down. One thing you may be mindful of, especially, is depending on the ball that you're gonna use, I'm using this nice soft Nerf ball that if it falls on the motion detector, it's not gonna be a problem. If you're using something like a basketball, something harder, you might want to use like a cage. And this picture here in the slideshow has come from the lab. It is just actually just like, this is literally like a wireframe inbox sort of thing that you would get from Office Depot. You know, that's all this is. You just need, this is nice because the sound waves can still pass through this, but if the ball lands on top of it, you know, this takes the damage and the motion detector does not. So you can put that over top of your motion detector, and as long as the wire frame is loose enough, you know, your motion detector is nice and protected. I'm going to go back to graphical analysis here. I'm going to do a new experiment here and go to my ball toss. So now I've got it pointed towards the ceiling, and I can tell at this point that the ceiling is just over 2 meters away. If I hold my hand over top of here, I can see, yeah, it's pretty good. Now, one thing to be mindful of is to remember that this, the thing that you're tracking, you want to track is the ball and not, say, your hands. So when you throw the ball, you got to get your hands out of the way. You also want to be careful that you want it to be as straight up and down as possible. This is one of those times when if you've got students on the basketball team, somebody that has a good ball handling skills, this is a great place for them. Have them demo it because they get pretty good at it. I'm going to switch my camera again here. Oh, you remember there's that dead zone. You don't want to get too close to the motion detector. It's about 20-30 centimeters. So that means you don't want to start with the ball right on top of the motion detector. You want to start a little ways up. And when I toss it, I'm going to actually do this silly thing and move my hands out sideways when I throw it up, just so that I can keep my hands out of that cone, just so that it's only tracking the ball and not my hand. And your chances are you're going to get some noise when you do this one. It's just kind of like the way it is. Your hands are moving around there. There's kind of lots of stuff happening. And that's okay. You know, usually you have the run, it runs for 5 seconds. You can often do more than one toss during those 5 seconds. And you really only need one good throw to be able to do the analysis that you'd like. So I'm going to do the same sort of idea. I'm going to hold this right here. I'm going to hit collect, and then I'm going to toss it. And I'll probably be able to do a couple of tosses here in this first run. There we go. That last one was pretty good. For the most part, you can see, I'm going to zoom in on that last run there. You can see there's kind of some noise here in the middle of it. This is probably me getting too close or whatever. And this last parabola here, though, is pretty good. I'm going to zoom in on that so I can see it a little bit better. And so I just selected the region there, and then I'm going to use the little zoom button in the lower left-hand corner. And it looks pretty good. I do have this like spike here. You know, that might have been me. It might have caught the ceiling there for a sec while I was, you know, catching the ball. You can kind of see that it's this nice parabola, and then there's a little bit of a hook here. That's probably where I caught it and was slowing it down. I'm going to just select these data points here, and I'm going to use the strike through option. This is a pro option to get rid of it. It doesn't actually get rid of it. It just excludes those from any sort of analysis that it does. And now I'm going to use my auto scale again and zoom in on that section again so that it looks nice and pretty. So now I have this nice parabola. And in the lab, what you do is the students look at the velocity graph of this section. Likewise, you can also, I'm going to just do a curve fit real quick here to show that it matches a nice parabola. So this is all these analysis options are in that graph options menu in the lower left-hand corner. I'm going to choose apply curve fit, and it defaults to linear, but I'm going to choose quadratic and hit apply. And you can see that light pink line is was the fit right there, and it fits pretty darn good. The root mean square error is really small. The fitting parameter A, which is equal to 1/2 of the acceleration, worked out to be 4.66, 4.7, which is almost half of 9.8. Often when you use a motion detector to measure the acceleration to the gravity, you'll get close, but you won't get exactly 9.8. It's hard to get that. There are lots of little things that might be happening there to get one way or another. Likewise, usually with the data that you get, the motion detector data that you get it's never like a perfectly straight line. And that's just because people and things that we track here are hardly ever moving in just a purely straight, constant velocity motion or purely accelerated motion sort of thing. So you get a little bit of wobble there. But that's okay. That's real world. That's experiment. That's doing science experiments. That's the way it is. And that doesn't mean the science isn't correct. It just means that our models might be somewhat limited. All right, so that's the ball toss activity. Students often, I love this activity in my classroom. I love doing this activity in my classroom, especially since we would do it in the fall, and then we would do it in the winter when we were talking about the law of conservation of energy, and we would do the same activity, but we would use the position and velocity data in order to put gravitational potential energy and kinetic energy graphs and total energy graphs. And we could talk about the law of conservation of energy. All right, the last experiment that I want to do is I want to show you a collision experiment between two carts. Cart and track experiments are often, are pretty popular, and you can use motion detectors to do that. You usually use 2 motion detectors. And so what I'm going to do is I'm going to set up a track here that has 2 motion detectors and 2 carts. And to do that, I'm going to push the chair this way. I'm going to pull. Okay. So let me talk a little bit about the cart and track system. I'm going to stop sharing so you can see this a little bit better. Most of our cart and track systems all have, this is our dynamics track, little feed. They come with carts. These are kind of our relatively new plastic carts. These are not sensor carts, so they don't have any of the internal electronics to measure their own motion. But they roll well. They've got magnetic bumpers, or like I've got Velcro tabs installed on this particular cart so that I can do inelastic collisions. They want them to stick together. Our cart and track system comes with these little, they're little reflectors that magnetically stick to the back of the cart just to give it a better, just so the motion detectors get better reflection off of that. And we'll put those guys are going to roll back and forth on the track here. The parts, the cart and track system comes with, these are masses that are designed to go on the carts themselves. So you can vary the masses between them. I have a green cart here as well, also that has one of those reflectors. They also come, the carts and tracks also come with these. They look like just regular rods, but they're designed, they have threaded, they come with a screw that's designed to thread into the back of the motion detector. So now this motion detector, the Go Direct one, as well as the regular motion detector 2, they all have a threaded hole in the back. That's a 1/4-20 threading, a pretty standard threading. And that's so if you wanted to, you could attach it to something like this rod. The reason why we attach it to this rod is so that we can use up the whole track. We don't want to, we don't want to lose 20 centimeters of our track, because that's like the dead zone of the motion detector. You can also use that threaded hole to connect the motion detector to other things. So I know instructors that attach the motion detector to a ceiling and have it pointed down towards the ground, and then have students jump beneath the motion detector in order to measure their own, how high they're jumping, that sort of thing. That's really nice, especially if you do, I know somebody mentioned in a question when they registered, about the air resistance coffee filter lab where you drop coffee filters. If you've got it on the motion detector on the floor and you're dropping the coffee filters above it, it can be kind of hard because they tend to drift a little bit. And it's easy for them to drift out of the cone that it can see. But if you have it mounted on the ceiling pointed down and you drop your coffee filters beneath that, it's much easier to track those coffee filters and it's much easier to get nice clean data out of it. I've got this motion detector now connected to this mounting rod, and I'm just going to slide that into the end of the track. And I'm going to leave it about 20 centimeters out so that it can track my cart pretty well. And so I've got, it looks like it's just barely out of screen here, but there's a motion detector on each side here, one for each of my carts. And one of them is already connected to graphical analysis. I'm going to go share my screen now so I can talk to you about how this is set up in graphical analysis. But that's kind of the idea. I've already leveled my track. I got my motion detector set up on both ends. I'm going to put my carts here in the middle of the track, and we're going to set it up in the software next. Okay. All right, so I'm going to go back here, new experiment. And I've already connected to one motion detector. I want to connect to my second motion detector. I'm going to connect wirelessly just because these are farther away from the other one. This motion detector, its ID code ends with S0. I'm going to find it. Here it is, S0, and connect to that. And there are a couple of things I'm going to do here before I move away from the screen. The first is, I know that I want to, I'm tracking carts, dynamics carts. They're relatively small targets compared to, say, myself or that Nerf ball I was using. So I'm going to choose under sensor channels here. I'm going to choose the cart channel, motion and system cart. And I'm going to do that for both. This, like I said, the threshold is a little lower, so it's listening for quieter reflections. And then the other thing is, you'll notice I want these two carts. You know, I want the center of my track to be 0, 0. You know, I want it to be that 0 on my number line. And the motion detectors to tell you how far away the object is from it. The problem is they're pointing towards each other, and so they're not on the same number line, so to speak. They're not using the same coordinate system. And so what I'm going to do is, in the software, I'm going to 0 each of them. I'm going to say, I want you to call this position right now 0. And I'm going to reverse one of them so that they're pointing in the same direction. That their coordinate systems are pointing in the same direction. So I'm going to go here. I'm going to 0 this guy. I'm going to go here and 0 it. And for this second one, I'm going to reverse it. So now these two together, if I move them, you know, they read about the same thing. They both read positive or they both read negative, about the same amount there. I move it back to 0. And for this lab, it has students look at inelastic collisions, partially inelastic collisions. That's where, you know, in the inelastic collision, they use the Velcro tabs so that roll along, they stick together and then roll off together. In a partially inelastic one, they just kind of bounce off each other a little bit. They slam into each other, and this guy kind of. And then they use magnets to do an elastic collision where the magnets magnetically repel each other, and they bounce off real nicely. And if you really wanted to, the sensor, one of these carts has the plunger cart has a trigger on it that you could have super elastic collisions where the plunger is triggered in their collision, and you end up with a really cool explosion sort of thing, and you end up with more kinetic energy than you started with. It's kind of cool. All right, so I'm just going to collect around data here, just with our elastic collision. So I'm going to move this guy, start this guy the green card over here. I'm going to hit collect, and then I'm going to push it, and it's going to collide with the stationary gray cart. and we'll collect some data. So I collect. All right. So there we go. It looks like I got some pretty clean data there. I'm going to make this a little bit. I'm going to auto scale this here so we can see a little bit more. You can see at first, both carts were stationary. Neither one was moving. This little point right here is when I push the cart. The first cart, this is the green cart, and it travels at a constant speed. And at this point right here is when they collide. And then they move off together. And it's interesting, you can actually see that they diverge here a little bit. And the reason for that is the gray cart actually pushed my motion detector a little bit. So if I were to do this again, I probably would want to re-zero them together just to make sure that they're still, using the same coordinate system, that sort of thing. And I could redo this again. In the lab, it has students do this a couple of times. They might vary the mass of either the target or the launched cart. You do it with the Velcro tabs, without the Velcro tabs, where they're just colliding with each other, with the magnets so that they magnetically bounce off of each other. And you can add in the super elastic collision as well. Like I said, that this gray cart has a plunger on it, and there is a trigger that you can use that's on the face of the cart itself, so that when it runs into it, the plunger is triggered and it launches itself. It's kind of a neat variation on that. All right, so I've talked a little bit about how this works. We've looked at a number of activities that use the motion detector, and some of the ins and outs of those particular activities. Well, I'm going to stop sharing here. And what questions do you have? Happy to address anything that may have.
Josh, one person asked, their comment was, so you would ask the students to take the slope to determine the velocity?
That's how I would have done it. You could also, I'll show you here, I'll share on here, because the motion detector is, all it's recording is position, and the graphical analysis app is actually calculating a whole bunch of stuff. So if I'm going to go here and click on the vertical axis label, and you can see that I actually have a position, a velocity, and acceleration for each of those carts. So I could turn off position, and I could look at just the velocities of those two carts, and although, here we go. Velocity to, I'm like, where's the second velocity data is right there. It's matched, they're equal to each other. So it calculates all those things. If you want to see both at the same time, I'm going to go back to position. Over here in the view options, you can show two graphs. And here we go. We'll make this guy bigger. You can see the velocity data and the position data together if you'd like. And yeah, there's my velocity. So yeah, I tended to, I prefer to have, I don't usually talk didn't talk a ton about velocity or acceleration graphs, just because I liked reinforcing the idea that the slope of the position graph is velocity. And you can either have them select a portion of the graph and then do a curve fit, a linear curve fit, and get the velocity that way. You can see here for my, this is the green cart here. It was about 4.4 meters per second. You can also, if you want to talk about in more of like a graphical sense, you don't want to have to go through that. There's an option in the graph menu, graph options, to you show the tangent line. And when you, that's where you click, it'll show you the slope of the curve at that particular point. And you can see that as I click along here, along that portion of the graph, it's about 0.4, a little bit below, a little bit higher. And then if I go over here to where they're stuck together, it's about, looks like it gets to about 0.2 or so.
Josh, one person asked if the bumpers, if you interfere with the data, cart bumpers, they ask,
Bumpers.
The track bumpers interfere with the sensor.
Not really, they can. So often with if I use this, my older motion detectors, these are the ones, the kinds I used in my classroom. I found that when I would collect cart data, rather than pointing it, having the pivoting head here, like say perpendicular to or parallel to gravity or perpendicular to the surface, I actually pointed it up a little bit. So it was like that cone was more pointed, kind of one side of the cone was pointed along the track rather than like pointed up a little bit. If you, depending on what you have on or around, sometimes, like especially if you've got an end stop here, that might block your the signal from it. Usually we don't have you, especially if you're doing collision labs, you don't usually have an end stop on there. If you've got things attached to the backs of your cart, some people actually will have made targets like this themselves to make things a little easier. Sometimes we would tape notebook cards to our carts to make them a little bit easier to see. And depending on the lab that you're doing and how you want to do it, sometimes you want just elastic versus inelastic collisions, and you don't want to, you're not talking about that in-between stage. In that case, you would really want to use the Velcro or the magnets. You don't want to do something else. Tamara asks, if you angle it, do you then have to correct for the angle and the slopes? You do not have to, because even though it might be pointed up, the round trip time that it's recording is still just from it out to the cart and back. It's like it's still that straight line distance. It's not like you're getting a hypotenuse or anything like that. And so the velocity, the position velocity measured by the sensor is still the position and velocity of the cart. Other questions about motion detectors or how we would use these motion detectors? I mentioned
there was a little confusion about, when you set the 0 position, when that gets reset. I tried to answer in the chat, but you might clarify that. One person thought every time you did a run, it would re-zero.
Oh, I see. Yeah. Once you set it once in the software, then it's basically just applying an offset. It says, okay, at this point, I'm going to call it 0. So I'm going to add or subtract this amount from all of my position calculations to get that point to always be 0. The only time you would need to re-zero is if, like in my particular collision here, where the cart bumped the motion detector at the end there, and then I ended up, that kind of moved where its 0 had to been, so then I would have had this re-zero at this point. But if that's not happening, if the motion detectors are where they've always been, and you've zeroed it once at that point, then you're good to go. You've got your coordinate system set up, and you can move those carts back and forth and have them bounce off each other and however, without having to re-zero. If you were to do that activity where you have the motion detector mounted on the ceiling and it's pointing down and you want to jump beneath it, it can be a little confusing with the default settings just because you're moving closer and then getting farther away. So the curve would be kind of weird. So you can actually have it pointed to the ground and then zero the ground, call it ground 0, and you can reverse it. And then when you jump beneath it, you get a positive curve like you'd expect. Laura's asking about whether the student laptops will connect easily with the motion detector. It depends on the motion detector and it depends on the laptop. If it's a Go Direct Motion Detector like these, you can just plug it in USB and Graphical Analysis will find it no problems. If you want to use Bluetooth, you want to connect them wirelessly, then usually it works fine, but it kind of like if it's a student laptop, if your school is managing it, sometimes they turn off the Bluetooth or they restrict what that Bluetooth can connect to. In that case, it might be tricky. I often use USB because it's easy. You plug it in, it's right there, right? But if you if you want to use, like in this case, it was nice to have it wireless so that I didn't have those cords draped all over my setup here while I was doing it. If you have it looks like Tamara here. Yeah, if your district disables Bluetooth on the Chromebooks, you can still use these motion detectors, but you just have to plug them in USB. You know, you plug there's a port on the side there where you plug in a USB cable, and then you plug the other end into your Chromebook, and you're good to go. And Dave mentioned there we have yeah, you can use USB with those Go Direct devices. It's kind of nice because that's how they also charge. They all have batteries in them, and they have to charge.
So here's a challenge for you, Josh. Someone asked that you show the acceleration graph, and they want to look and see what happens there at the collision.
Okay, go 3 graphs here. Let's see if we make this guy big. Looks like the collision happens here, and you can see it's big for a little bit there, peaks out. It's a little hard because when things happen really fast, it's doing a numerical derivative, and so you don't always get, it kind of rounds off peaks, you know, kind of it tends to amplify noise, and so you tend to fast changes, it doesn't work real well. But this is where they collide, and then at the end here, this is where they came to the stop at the end, and where that second cart kind of collided with the motion detector. But you can see, like I said, it automatically calculates the velocity and the acceleration here. But by default, it only shows you position. Let's see. If your student laptops only have one USB port, do they go? Oh yeah, yep, they'll work just fine with a USB hub. You know, just like, you know, often they'll have a hub that has 4 ports on it, something like that. You can use one, you know, it goes out to your student Chromebook, and then you got 4 ports there. That'll work just fine. The TI-84 calculators don't work with this Go Motion or Go Direct motion detector. They do work with a different version that looks like this. It's gray. It's the CBR2, and it'll plug into the TI-84 calculator. It's like I said, it's gray. It's called the CBR2. I think that's for calculator-based Ranger or something like that.
That's right. Hey, Josh, I would add that we are now working with TI, and this fall we'll have a way to use those sensors with Python on the TI calculators. And I think it wouldn't be surprising if down the road we had some other things coming.
Yeah. Tamara asked a question too about like the LabQuest Mini. Let's say I have this already, and I want to get new motion detectors. Maybe I only have a few that still work or whatever, and I want to get new motion detectors. Do I need to get more of these, or can I use these Go Direct motion detectors that are nice, fancy, wireless, and Bluetooth and all that with them as well? And the answer is yes. You could have, especially at an experiment like this where you're using 2. Maybe you only have one regular motion detector and you have one Go Direct motion detector. You can plug them both or connect them both to Graphical Analysis, and Graphical Analysis will sync the data together and collect the data from both. It doesn't care whether one's Bluetooth and one's using a LabQuest Mini or what, that they all work together. Sometimes you'll need to do that because you've just got different generations of probes, and but you can make it work. All right. Well, I'll say just by way of reminder, this webinar was recorded, and in about a week or so, you'll get an email. We'll post it to YouTube, and you can find it there. Please, if you've got questions, you feel free to reply to those emails or reach out to us. Like I said, if you call or email or hit us up in the chat window on our website, I'm one of those people that answers those questions. I'm happy to talk to you about it. We understand that school budgets are not unlimited, and that these probes really are an investment. We want to make sure that you get the most out of them. So if you have questions or something's not working for you the way you expect, please reach out. Let's make sure we can get it working so you can get the most out of your probes here. Thanks again for coming, and we'll see you with our next webinar.
Thanks, everyone. Bye now.